Previous video, we had an example where we were asked to find the antiderivative of x squared times the cosine of x cubed plus 5. And by doing a u-substitution, we saw that this went back to the sine of x cubed plus 5 divided by 3 plus a constant. And the technique that we used was called u-substitution. In this video, what I want to do is I want to look at the theory of u-substitution and see why it really is doing nothing more than undoing the chain rule. So to get started, I want to consider this particular problem. I want to think about the fact that d dx of f of g of x is always going to be known to be the derivative of f evaluated at g of x times the derivative of g of x. And this, of course, is the chain rule. Now, just in terms of antiderivatives, the fact that we've got that derivative, the antiderivative of f prime of g of x times g prime of x dx is going to have to be the function that we just differentiated. It's f of g of x plus any constant that we want to add. These two things are simply saying the same fact in different notation. So the question is how can we go from this particular antiderivative to this particular answer for the antiderivative problem without actually having a formal derivative sitting in front of us. So I want to start off with just looking at an antiderivative. So the easy case, if I have an antiderivative of f prime evaluated at g of x times g prime dx, I already know what that's going to be, but I want to formally look at some notation. So I'm going to let u be equal to g of x. Then du dx is g prime, and converting that into differential notation, du becomes g prime times dx. And what I'm going to do is I'm going to substitute these things in for that particular integral. So this is going to go in for there, and this is going to go in for g prime times g of x. And so the integral gets rewritten as the integral of f prime times u du, and the antiderivative of f prime is simply going to be f evaluated at u plus any constant that we want to add, and now we back substitute. U was nothing more than g of x. But of course, how does this work in practice as opposed to the most standard kind of an example? I mean, this is clearly illustrating that we just undid the chain rule. So now what I want to do is I want to look at the more practical way of how things look. So a more general set of symbols. When are we going to be wanting to use u-substitution? Well, suppose I've got a function that looks sort of like this. I've got some kind of f, but I've got some kind of mess in here that I'm going to call g of x. And I've got some other function that is going to be called h of x times a dx. But what I notice is inside my integral that g prime of x turns out to be awfully close to h of x. The only thing is it's not quite equal to h of x because there is some kind of a constant. And I'm going to call this constant, let's call this constant the number a. So I notice that what I'm looking at in pattern is that this is almost, but not quite, g prime. So when I have this kind of a situation, what I can do is I can say that I will let u be g of x. I will calculate du dx. So I will calculate du dx is equal to g prime of x. I will notice that this is equal to a times h of x. And I will notice that du is equal to g prime of x, which is times dx. Let me make my notation clearer because I have converted to differential notation. And that this is actually a times h of x dx. And what I'm going to then do is I'm going to fiddle with my integral. I'm going to rewrite this integral as a over a times the antiderivative of f of g of x times h of x dx. I will bring in this top a through the integral sign. And when I do that, I've got 1 over a times f of g of x times h of x dx. And now I'm going to simply circle some things. This plus the h of x dx all goes together and forms a du based on this particular stuff that we've written down. And this here is going to go in right there. And when I do that, my integral is going to become 1 over a times the antiderivative of f of u du. And that will go back to whatever the antiderivative for f is. I'm just going to write it as capital F. So we have capital F of u plus c. And then our final answer will be capital F at antiderivative for little f, evaluated at g of x, divided by a plus a constant. Now, it is traditional to also block off the stuff that we are writing for the u-substitution in a box so that it doesn't get confused with the calculation of the integral. So the net result then is that we have that the antiderivative of f of some kinds of junk times something that's almost equal to the derivative of the junk can be patched up. Now, there is one warning that I want to put in, and I'm going to just add that right here. The warning. The only thing we are allowed to bring through the integral signs are constants. So u-substitution only works when that h of x stuff inside the definite integral is a constant multiple of the g prime, which is whatever where g of x has been called u. In other words, if I have anything else missing inside the integral, I can't do u-substitution. We will look at that in an example in another video, but I want you to have this warning down in your notes.